Okay.
Sounds good. So hello, welcome everyone. Very pleased to have Federico today with us to talk about like low power SNN applications, different ones, just on the edge. Data capture is captured near the edge of the sensor. So yeah, this talk is hosted by Open Neuromorphic, online community of open source, open hardware collaborators. And this Zoom session is sponsored by TU Delft. Thanks for hosting that one, TU Delft. And yeah, I'm just going to give the stage to you directly, Federico. And yeah, that's it. Thank you.
Thank you very much, first of all, for the kind invitation. I really appreciate this open neuromorphic community, I have to say. I've watched some of the videos, some of the tutorials online. It's great to see lots of nice work. I'm going to share my screen now, and let me know everything is okay. You should be able to see.
I can see your screen. Great.
Okay, great. So thank you. So today I'm going to talk about low power SNN processing systems for extreme edge application. I'm at TUE, so Eindhoven University of Technology, and I'm an assistant professor here at the Department of Electrical Engineering. And my lab works on neuromorphic edge computing system. And I will show you what we do in the next few slides. Feel free, of course, to interrupt me if you have any questions along the way. I think it's better to be a bit more interactive. Also because some of the topics that I will cover today are of high level, some of them, but if you're interested in details, we can always discuss also during the presentation or even later on. So the outline of today, I want to introduce you what I mean by edge artificial intelligence. And then I want to show you one architecture that we developed called the microbrain, and then a couple of applications that we can cover with this type of architecture. One is on radar signal processing, and the other one is on biomedical signal processing. And then I want to tell you a bit of what's coming next and what can we actually scale up to larger applications. So today, the field of edge artificial intelligence, the main thing that requires is the executions of real-time and low-power artificial intelligence, which is a very big challenge because it spans very many, let's say, applications from biomedical, in which you have, for example, monitoring devices attached to the body or even inside the body. Mobile devices, you want to interact with mobile devices, navigations, and even fast autonomy. And these are increasingly, let's say, complex and require increasingly more powerful systems. So let's say the requirement that we have is that we need to behave mostly in real time. So we need to have real-time operations. Typically, these are battery power, so we require very low power systems. And we need to consume the data locally. This is for privacy reasons, especially for biomedical applications. Moreover, this type of AI intelligence requires increasingly complex neural network, and in order to increase the intelligence and autonomy of the system. Also in biomedical, if you can think of that, it would be very nice to have very large network that solve very complex multidimensional tasks. But today we are limited to simple networks. And so what do we do about it? So there are many approaches that people are actually looking at today, not only in neuromorphic. There are traditional machine learning approaches, there are brain-inspired model of computation, and there are competitive computer architectures. And these are like fields that try to address, to lessen the computational burden for running AI models. What can we do? Well, people are actually building hardware accelerators, also for traditional DNN, let's say. And people are actually looking, and researchers are looking at how to compress neural network into tiny neural network that have small memory footprint and small computational footprint in order to fit them into tiny devices, like, for example, microcontrollers or tiny devices as such. So network compression is actually a big field today. And there are new neural network architectures that that are being proposed that try to minimize memory access and as well as computing memory. For example, mobile net, efficient net, all these type of network are actually there because they want to be applied at the edge. Of course, there are also new type of design styles that we are seeing today. Like, for example, analog in-memory computing in order to increase the computational power of AI accelerator, for example, for doing matrix multiplications or for doing operations that are actually required in many of the DNN accelerators. But myself, I'm actually interested at the intersections of these three fields. And in particularly what I focus on brain-inspired computing model that are spike-based. And I focus on spike-based neural network because I want to look at the long-term challenges that we have in order to try to embed intelligence into edge AI devices. And I want to take a brain-inspired approach as well. And so I'm not the only one, of course. In this field, there is a lot of, and we have seen it also here at the Open Neuromorphic, there are lots of approaches, and there are many, many companies and research laboratories that are now looking at neuromorphic computing within these intersections of these three fields as a way of covering edge AI applications. There are many companies like, for example, IBM, Intel, the Human Brain Project, IMEC in Natera, SNNs, we have also seen here in Open Neuromorphic. And all of these chips, all of these devices, they have something in common, that they are inspired by neuroscience and neurobiology. They leverage advanced semiconductor node technologies. For example, Intel Loihi, with the Loihi 2, they actually use 4 nanometer technology, if I'm not mistaken. So it's a very advanced process node. And they combine analog, asynchronous, and digital logic circuits, many of them. And they are made to run edge AI applications at the edge, like robotic application in which you require real-time, low power, consume the data locally, and what we said before. Let's say, typically what we have seen so far in the past 20 years or so, we have seen different approaches. There is one approach that is the one on analog and mixed signal devices that is mainly, let's say, taken by the Human Brain Project with the Brainscale mixer signal chip from the University of Zurich, Professor Giacomo Indiveri. For example, there is a startup in Natera that is working on mixed signal analog chips and for spiking neural networks. And these have the benefit that can have a very high level of biorealism. Actually, you can mimic with the physics of the silicon, the same processes, neurobiochemical processes of neurons and synapses of real neurobiological systems. And so you can implement long time scales, and they can be ultra low power for this reason. So these are some of the benefits that you get, especially because you want to have an isomorphism between physical computations in these devices and physical computation in neural systems. However, you have to pay a price for that. And the price is that they are sensitive to noise because those are analog signals, so process temperature variations, and they are expensive because in order to be there, to have an isomorphism, to have a physical means of computation, you need to implement physically all the neurons and all the synapses, right? So they become larger in area. And also they require high design time because they're analog devices. So each of these components needs to be designed by specialized engineer that actually, it's an art to do analog design if you want. And so another approach is the digital approach. And the digital approach is the one that is mainly followed by large companies and also the Human Brain Project with the Spinnaker, for example, today. And in this approach, the benefits are that everything is digital. So you have a very high fidelity between your software model and the hardware. There is little noise. They're much denser than analog because you can leverage, for example, 4 nanometer technology or very advanced node technologies. And they enable a very fast design because we are using silicon compilers, meaning that we code at high level blocks, digital blocks, and then we can use silicon compiler to then design the full chip. And this enables a very fast design. So most of the time, the layout is hidden by the designer because it's actually a digital flow that goes through. And so the downside is that this type of processing systems, they all have memory and computing element still next to each other. And typically what they have is that each of these neuron core is a little von Neumann machine that shuffle data between the memory and the processing element. Typically, you have time multiplexed of one processing neuron that process 1,000 of neuron by keeping reading and writing the memory that is close to it. And this you can find in IBM, Intel, and also in the Human Brain project. And of course, the downside also is that they require large on-chip memory because, of course, you need to store the synaptic weight and to store the membrane potentials or the state of the neurons. And so one of the approaches that I propose as an alternative one, and that we started actually developing a few years back, is an approach that is a mix in between the two, the analog and the digital one. And this is a synthesizable mixed signal, in which what we do, we design fully asynchronous systems in which we design analog mixed signal cells that then we try to integrate into the digital flow process. And by doing so, we can benefit from it because we have still high fidelity between software and hardware, because in the end we still use a digital flow, but we are able to achieve fully asynchronous systems. And we still have a fast development to deployment cycle, meaning that because we use silicon compilers, we can still enable the creations of chips just by changing parts of the code. And in fact, we realized two different chips that are based on the same architecture. One is called microbrain, and you see a picture here. It looks like a spaghetti matrix because there is no, it goes through a silicon compiler, so there is nothing that you can actually identify in this chip. And I will talk more in details about the architecture in the next few slides. And then we have designed another chip with the same spiking neural network architecture as the previous one, just with different parameters and with different sizes. And so this enabled us in less than 6 months, let's say, to have 2 tape out and to cover 2 different application spaces. The downside, of course, of this approach is that there is larger area, because now we are implementing all neurons and all synapses in the device. So they need to physically exist in order to be present. And because they are completely asynchronous systems, now there is the difficulty of training the spiking neural network, because training spiking neural network in which each neuron gets as soon as it reaches the threshold, emit one spike, so there is no barrier synchronizations between the different neurons in the network, creates challenges in terms of algorithmic how to train those systems. And maybe at the end, if I have time, I will show you some of the work that we're trying to do in that direction. And so now I will switch to the second part of the talk, and I want to show you a bit more in details the microbrain architecture and its component. The first component is the neuron of the architecture, and the neuron is a fully synthesizable tiny core, I would say. It's an integrate and fire neuron, so nothing new so far. You receive a bunch of input stimuli, spikes the neuron. It has a membrane potential that is a digital value encoded with an accumulator of the membrane potential. Here you can see it. And whenever it reaches the threshold, as soon as it reaches the threshold, it emits one spike, one output pulse, and then the neuron is reset to its resting potential. The neuron, importantly, is self-timed. It is completely asynchronous. And it contains 3 main blocks. There is one block in which there is an arbiter and a spike detection mechanism. we have a weight selection block, and then we have an accumulations of the membrane potential block. The spike detection and arbitrary block takes care of detecting incoming spike for the neuron, spacing them in time so that then the accumulation of the membrane potential has enough time to perform all its operations. So selecting the weight and performing the accumulations and thresholding operation, right? So what we can do with this type of neuron, we can, of course, program the weight. Those are in a digital logic. It is scalable now because we don't have to propagate any clock, but each neuron only receives spikes and emits spikes. And when it receives spike, the spikes get spaced in time so that the neuron has enough time to perform its operation. Of course, there is one big assumption here, and the assumption is that the arbitration delay are in the order of nanosecond, and this is what we will achieve, while incoming spike are in the order of microsecond or even millisecond, right? So the incoming spike rate is less than the arbitration speed, so that then we can actually accumulate the membrane voltage and serve all the spike that arrive at the neuron. So if we can assure that, then this is a good and scalable neuron model, because then we can just implement it and scale it to very large network. Importantly, as I just said, that the arbitrations or the arbiter block in which you have a spike detection and an arbiter is a fundamental block for the neuron and enable it to be asynchronous. So I want to show you a bit more in detail this block. And this block enable self-time arbitration, meaning that upon the arrival of incoming spikes and throughout their consumptions, the arbiter circuits become a non-demand and self-clocked by means of a multi-phase single cycle oscillator and a special delay cell circuit. What does it mean? It basically means that whenever the neuron receives spikes, there is an input edge detector here that detects the incoming spike and immediately activates spike register and a go signal. This go signal activates a multi-phase oscillator, and this multi-phase oscillator contains, produces timing signals with specific phases. And this timing signal, what they do, they basically enable the select and the spike, this line here, and the spike is then sent to the accumulations of the membrane potential with certain spacing in time, so that then the accumulations of the membrane potential can be executed without having to, can be executed fully. So this, yes, you have a question, Fabrizio?
Yes, just a quick question. So as far as I understood, this is supported mostly because the neuron is an integrate and fire one. Because if it was a leaky one, you still needed to have a concept of time in some sort to have a specific time step. So do you see a way in which this kind of hardware can support a more powerful model, such as a neuron with a leakage? That is, I think, the same principle that drives the spec architecture from SNNs.
Yes, that's a very good question, actually. So the leakage, the way in which we implement it right now, we only have, let's say, an inhibitory synapse, and then you have a spike coming from outside. And then if this is regular, then you can implement a leakage. So it's a very trivial way of implementing a leakage. However, it is true, right, that this mechanism of self-time multi-phase oscillator could also be used as a leakage mechanism. We didn't do it for this circuit specifically, or you can imagine that you can now change the accumulations of the membrane potential. Instead of having it in a digital accumulator, you can make it on membrane capacitor, right? It's like in analog, and then you can use the current that discharge the capacitor with a certain time constant, and then you will get a leakage. Of course, this is a different design, but everything is possible. What we wanted to do in this specific design, we wanted to first demonstrate that it is possible to go through the digital flow with analog mixed signal cells, and we get we wanted to achieve very high fidelity between software and hardware. Therefore, we decided to implement the neuron as much as possible in digital, and only the timing information, let's say the spacing of the spike, required an analog cell in order to be scalable and completely asynchronous. So we really wanted to be as close as possible to the digital world, because we wanted to have very high fidelity and not having to deal with noise and small currents and things of that.
Yeah, I feel you on that side, because I'm a digital designer too. Actually, it will be really interesting to see if what you mentioned could be implemented with embedded DRAMs that are sort of analog and sort of digital, but at least there is some flow, because they leak by themselves. Okay,
yes,
thank you.
There are many mechanisms, right? So, but in this specific one, we wanted to, try to, is for the first time, try to have it an asynchronous compiler with the standard tools, right? So we were only constraining them. But okay, thank you. If you have more questions, don't be shy, interrupt me. Also from the audience. Huh? And yes, so basically what we did, so we had this 3-phase clock, right, or 3-phase timing system that enable us to have the neuron completely asynchronous. The multi-phase oscillator cell is actually a simple cell. The concept of it is simple. I will explain it now, the concept, and then I will show you some measurement about it. So the concept, it's basically a PFET and an NFET. So you have 2 transistors here. And you have a current source, or something that sinks the current from the circuit. I'll go in the details of this, but if this gets recorded, then you can skip it if you don't want, if you're not interested. But the idea is the following: so that a thyristor, that's what we use in this circuit. Actually, we use a couple of them, but I will explain you only the functioning of one single one. So it's called tyristors in CMOS, and it's a PFET and NFET, and then you have a current source. And you have some switches, the control switch, S1, S2, and the N1 control switch. So at the beginning, you can imagine that S1 and S2 are closed. Therefore, you charge, and control is disconnected. Therefore, what happens is that this node at the PFET gate is a VDD, and this node is held at ground, right? When S1 and S2 are actually opened, the node not Q and the node Q stays where they are because they are undriven, and because the voltage is retained through the gate capacitance. And what happens is that when you want to generate a delay, you send a signal to the control switch, and when this is connected, then you see that this one will drain basically the voltage at the PFET, at the gate of the PFET. Actually, this should be Q, not Q. And when this one drops below, below VDD, this transistor starts to conduct and starts to charge this one, this node Q. At this point, what happens is that this will also open, and then it is a positive feedback, and this M2, this Q will increase, and then will open M1 as well, and then will be discharged, the gate capacitance. So basically, there is a delay that will end when the not Q is at ground and when Q is at VDD, right? And actually, by setting how much current, this is a small current, right? You're sinking through this current source, then you can basically make a delay between the control signal and the Q output. This is a very simple mechanism. Of course, what we did is slightly more complicated in the end. We used 2 thyristors coupled together, and then we also had a bias at the circuit in order that controls this tiny current that then discharges the node. And this is an analog design. This is the only analog cell that we designed in the full architecture. This analog design cell, then, because it's an analog design, we needed to have characterizations with as much as possible process temperature and voltage variation. And we did that also for different supply voltages, for different temperature. And what we saw that there are a bias voltage value of this node Vn that enable us to be always in the right regions of delays, so that then the spike are distantiated enough for the neuron to perform the operation before it gets the next one. And so what we did, we designed the cell. You have a question, Gregor? Or?
Yeah, so for someone who doesn't have a hardware background, so can you explain again why the delay is needed? Because I cannot feed all the spikes too close because there are the analog components, or
no, because the neuron takes some time to fetch the weight, to accumulate the membrane potential, and to evaluate its membrane potential against the threshold, and to decide whether you want to emit one spike. It's a physical system, right? So there is always some time needed in order to perform this operation, right? And so if you want to be typically in synchronous design, in digital design, you have clocks, right? And so clock tells you when to perform operations. And so it's pretty easy for you to say, now do this, now do that, and then, have a counter and say, like, execute the operation in sequence. But now anything can happen at any time. So spikes can arrive at any time, and you're not sure when they arrive because everything is asynchronous. And so what you need to make sure is that when you receive a spike, you're able to serve it. By meaning, you need to fetch the right weight from the synapse, you need to accumulate the membrane potential, you need to evaluate the threshold, and then you can decide whether you will emit a spike or not, right? We wanted this to be completely asynchronous, so we don't want to have a clock in our system because that's one of the major sources of power consumption, especially when you have edge applications that require let's say, low rate of input, or in which your on versus off rate is balanced towards the off rate. No, you can imagine, for example, I don't know, you want to monitor a room, but somebody's there only 8 hours a day. So why are you? Or things happens at different times, right?
Yeah, makes sense. Yeah.
To do that, we needed to have one single cell that enabled us to track time in a way that we give enough time to the neuron to perform his operations. That's the only thing that we had. And this is the arbiter spaces the incoming spike enough so that the neuron has enough time to perform its operation. This is exactly what you see here. Huh? So range is okay for us. It's enough, right? So the bias value here for all the process temporal variations, that's enough. We don't want too much, we don't want too little, that's okay for us. And then we can use and constrain our digital design flow within this range, within this boundary, let's say, without having too much troubles. So that's what we did, basically.
Cool, thank you.
And yeah, and then here you see us actually a measurement of the neuron. It's a digital, goes up, down, spikes, and it does all of its work. After that we were very happy with our neuron. We decided now, let's connect many neurons together and let's have a way in which we can program the synaptic weight. We also wanted to be as simple as possible, and we also wanted to be as precise as possible. So we went with digital flip-flop, so not very optimized in terms of area, but we wanted to test our framework first, right? Our architecture. And so we use a simple scan chain in which we connect in a chain weight selection, so the memory of the neuron, at which the neuron has, each neuron has a synaptic memory in which you can program it with 4-bit each synapse, and then we connect them with a scan chain, and then we can reprogram them from outside. So we just program them once, they stay where they are, and then whenever they receive a spike, then there will be a weight selections, and then the weight will be available at the membrane potential before the spikes come in. And this is why we have these 3 clock phases, right? And this is very nice because then we can synthesize it neurons with no memory macro. So the memory gets really distributed where it is needed. So you can have neurons with hundreds of weights, neurons with 10 weights, and then they get automatically distributed. We are not using SRAM macro block inside the chip. And that's why you also see this spaghetti type of picture when you look at the microbrain layout, because there is no singular SRAM anywhere. This might be not optimal for now, but this is a way in which we I mean, since synapses needs to be there, it's a way also of being completely synthesizable. Of course, we can change the design of the weight. This is not optimal. We know that the weight will require some area, but we decided nevertheless to do this tape out. And yes, you have a question?
Yeah, I understood that basically it's a register-based in-memory computing architecture. If one wants to look at it from an
Yeah,
external
I would not say
perspective.
memory computing in architecture, because it really, the memory is distributed if you want, and it's close
Yes.
to where it needs to be. But
Yeah, it's
we're
like
really using the
every cell
memory.
is intelligent. Every
Well,
cell is
we are
intelligent.
really using the memory here just a synaptic way. So it's just the jump that you do with at the neuron. So it's not really anything fancy, I would say. It's really a memory cell, right? Tunable
yeah.
device. Not a tunable device. No, it's not. It's a flip-flop for bit, and you can program it. And so what you see, for example, now we can do very tiny devices. Like this is a microbrain. The first microbrain chip that we did is 1.68 millimeter square. This is close to 1 euro cent. And it was done with 40 nanometer digital technology. And the only cell that we did to really do the layout was the delay cell. It comes out to be 60% of the area is actually synapses. We could have done something smarter there. Probably we will do that next. 4% of the area is the neuron, and 36% of the area is this arbitration. This requires some logic. We implemented 300 neurons, so a very tiny chip, 200,000 synapses, more or less. But the nice thing is that it consumes less than 100 microwatt of power. So now you can use this for extreme edge applications. And
I was wondering, with this kind of memory organization, are you able to deal with convolutions where the same weights are used on multiple input feature maps and to multiple output feature
good
maps?
question. So with this type of architecture, it will be inefficient because weight sharing is not something that it is implemented. And in fact, the type of architecture that we did implement is a multi-layer architecture in which you have recurrent connections on the first layer, you see it depicted here. Then you have a fully connected to a second layer, and then you have a fully connected to a third layer. So we have only 16 output from this device, and we have 300 neurons, 256 in the first layer with lateral connectivity, 64 in the second layer, and then 16 at the output layer. Also, why recurrent in the first layer? Yeah, so that's that could be, each neuron is its own oscillator, is a big overhead for power and area. It's really better than synchronized design. Yeah, that's a very good question, Liao. It depends on the workload in the end. And I will show you an example in which it makes sense for us to have this type of design against a synchronous state-of-the-art design for biomedical applications, for example. But this is a very good point. Keep this question for later on, then we can discuss at the summary. The thing is that, of course, now the architecture is fixed, so we cannot change we can program the connectivity by putting zeros or one. Please ask the question.
Sorry, I just reposted the
okay,
because
okay.
Otherwise not everyone is able to see it.
Yeah, and I was saying, yeah, so the architecture is fixed. You can reprogram the weight, through this IO. You just program the weight, and that's it. So you cannot do much about it, right? But it's asynchronous, and we have a very high fidelity now between the software and the hardware. Even if it is asynchronous, we have very good software to hardware fidelity. And so what did we use it for? The first act that we use it for, and this is because we were looking at human gesture recognition, for example, through radar signal processing. So you see the setup that we use to record a small data set with a transmitting antenna for a radar, transmitting a receiving antenna from a radar. And then, the radar is a small chip. What it does, it emits some energy into the space, and then the energy that backscatter from the space is recorded with a receiving antenna. And this is actually useful because you can see movement, you can see gestures, and you can see this type of human interactions. And so we collected the data set of 4 or 5 different gestures. We binarized them after doing pre-processing. And then we use these 28 by 28 small images, black and white images, as input to our network. And then the task is about classifying these different patterns. You see 2, 2, 1, 1, 3, etc. And those are different gestures. And so what you can see here, you see that you have the radar front end, you have your user command. This we record the ADC of the radar. We generate spikes by doing this binary matrix pre-processing type, and then we use them as input spike with the microbrain processors, and then we ask, and then we train the microprocessor, the microbrain offline, because there is very high fidelity. We download the weight, and then we can do this gesture recognition task quite accurately. So,
sorry, Federico, question
yeah.
here. So when you say like you have a high fidelity in software and hardware here, so when you train on your computer, like supposedly you're using a temporal resolution of, let's say, milliseconds or something like that, which accumulates multiple spikes in one time step.
No, exactly. Very good question. So we in order to simulate it, you need to have a very low temporal resolution in your simulation, hardware simulations, because that's what matters, right? And this is actually creates problem. And we'll see later on in the talk how we can deal with these problems, because once you train a recurrent network or once you train a spiking neural network for a specific time step, then you need to store all the activations in memory and do the backprop part. And so this creates problem. But for small network, like the one that you see here, 100 neurons, 300 neurons, 500 neurons, is still feasible to have very tiny, so they still fit in GPU, so you can still train those, right? And so, but a spoiler, with Bojan Ying, PhD student, and now is working in Natera, we address this problem of breaking the training over the time step and just using one single time step for training. But this comes later on. And so ideally, we have this fidelity. Of course, it costs a lot because you need to take into account very, very small time step, but you can get very good accuracy. And you can perform near and in-sensor computing. Here you see some of the measurement, of course. There's a planar, wave, radial, and the background gestures. And then you see 4 different output neurons from the microbrain that selectively respond to the 4 different gestures. So this is the membrane potential of the neuron, the spikes, and then you can see it there. And so now also going and answering the question that was from Liao, where does it make sense to do this, right? How does it compare with state-of-the-art edge devices, for example, for biomedical signal processing? In order to do so, what we did, we looked at the case of insertable devices. Now you have to imagine of a device that goes under your skin, close to your heart. And the task here is to monitor the temporal features of the electrocardiogram signals. And these are the complexes like the P, Q, R, S, and T wave or complex. The task is to always on is an always on monitoring task, and we need to perform temporal feature extraction for anomaly detection. So ideally, we want to know the time in between the PR, the QS, this segment, and we want to know whether it is present or it is not present one of these complexes. Because if there are heart problem, for example, and there are patients that don't have the T segment, this might relate to some of the dysfunctions of your heart. So it is important for us to monitor, and especially for biomedical cases, it could be that this is sporadic, especially at the beginning of the disease, right? So it is important to be always on monitoring for a long period of time, because you want to be able to catch these behaviors. And so what we did, we resynthesized the microbrain architecture, and now we did it with an even smaller network. We only used 100 neurons, fully recurrent, because that's enough for us to solve this temporal task. And still, it is a 40 nanometer chip with 1.6 millimeters square. As you can see, most of the area is actually empty, is filler. And we did also implement now a full system in which we have analog to spike converters. So now you have to imagine that in order to sense the electrocardiogram signal, we don't have a clock in our chip. So we also don't want to have a clock at the ADC. So we basically designed, together with Prof. Peter Harper here at the Eindhoven University of Technology, a very sensitive analog to spike converter. And what it does is the following. You see it here, you have a voltage input. Imagine that this is an ECG signal, right? You have the up and down output channels. So one signal gets converted into two streams of spike. And whenever the analog signal passes one of the threshold up or down, a spike is emitted in the up or down directions. What it does, this type of converters, it converts the signal into spike, and it also performs compression, because when there is no signal or when there is no ECG bit, let's say, you have a low density of spike coming into your device, right? And power of the microbrain relates to the amount of spikes that you need to process. Yes, Fabrizio?
Yes, this is really interesting because it's partly similar to what an event camera does.
Indeed.
It's a same.
We were definitely inspired by the event-based camera here.
Yeah, but,
and this is actually used in multiple places in the sensory systems, not only in the retina, but also the cochlea does that. You can imagine the touch does that, and also functions. And this is a pattern that is used, I would say, that you can see in many places across different sensory systems. It lowers the data rate, definitely, right? Because imagine now that you have to sample this signal with a fixed ADC. You always have to sample it. And the nice thing is that the electrocardiogram signal or our heartbeat, our human heartbeat, has to be within certain range, right? It cannot go more than 200 beats per second. So there will always be loss of 180. I don't know exactly the number, but cannot go higher than that, right? So there will always be, it will always be a sparse signal. And that enables us to let's say be active on demand, because we only compute the SNN when we have these jumps and these complex features of the PQRS and T. The functions of the remaining area of this chip, there is a question. Yeah, so we were really not using them. It's just because we had many pads that we wanted to probe a lot of things in this chip, and so that's why the chip became much larger than what it's supposed to be, because it's a test chip and we wanted to have many pads for testing. We also have another body channel communication, so there's more radio implemented in it. I'm not going to explain this too much. It's a simple circuit. Actually, it's been developed by IMEC with Yahong Liu, and transmits in pulse-based transmissions the different spike output from the device. So it is really an implantable device. Right? It can really go inside and communicate in ultra low power using ultra wideband pulse-based ultra wideband communication. So even the radio doesn't need a clock now. It just communicates whenever it gets its own signal. And so yeah, so we resynthesized the microbrain. We only needed 100 neurons to solve this task, 7,000 synapses, and we did that with less than 50 microwatt of power. And we had to innovate and to have these analog to spike converters completely asynchronous in order to make use of our architecture. And so what you see here, those are actually measurements from the scope. And what you see is that we can tell you P, T, Q, S, and R. So those are like 1, 2, 3, 4, 5 different neurons that respond to different phases. Because the oscilloscope only had 4 channels, we had to use 2 of them for 2 of the channels. But these are really different neurons that answer, because we have 16 neurons output of the chip here. Actually, in this one, I think we only had 8. And so we do temporal feature extractions, and we have an accuracy that is less than 1 millisecond, right? And this is something that we measured at the scope. And this is very interesting, because if you have a 256 kilohertz sampling rate, right, you already have a latency of 4 milliseconds because of your sampling. But because you're asynchronous here, you can go faster. And in fact, now this will answer the first question that was from Liao. how does it compare, right, to having a digital system with a clock? For this specific case, well, if you look at the precision in milliseconds, it's faster. So we have less than 1 millisecond precisions. Other systems have 4 milliseconds, 2 milliseconds. We do the full labeling, PQRS and T shapes. And in power consumption, it's very, very reasonable, and it's actually outperforming some of the state of the art for insertable devices. So it is a very good device, at least in terms of power. And so the SNN for chip monitoring, for feature extraction, it is ultra low power, and it is faster, or the fastest in this case in this table, because it is really asynchronous, right? And so in summary, for concluding the first part of this talk, is that asynchronous tiny spiking neural network chips for IoT, like radar, gestures, always on, and biomedical signal processing achieve competitive performance today already. They're always on, they are ultra low power, they consume the data locally, and they're ASIC for specific tasks. As I said, and as Gregor actually asked, this is nice, right? But how do you make sure that you can train now large network, and how can you make sure, it becomes very expensive to have very tiny discrete time step. It becomes unfeasible to train very large network at some point, right? And now I want to show you some of the recent work that we did with actually with Sander Botte, Professor Sander Botte and Bojan Nguyen, for training end-to-end large-scale SNN. And this also is one of the problems that we had with the microbrain. So we are able to train, right, this type of devices if the network are small, because otherwise memory explodes. And so I think in this audience will be clear, that the neuron, the computational graph of leak integrate and fire neuron, you have input coming in, you have the memory potential UDT, and then you have the spike coming out. And then you have a reset mechanism that is the red part here. So this is basically the computational graph, right? Will you please take more training deployment of ECG detection? Thanks. Yes, so to train the ECG, I will show you how we did it in here. So we used data set that is from PhysioNet, for example, in order to compare the accuracy of our system. So it's actually an available data set that everybody uses in biomedical in order to compare their own systems. If you're interested also in details, by the way, we published that work in Journal of Solid State Circuit 2022. So you can also find the publications here. And when I will give you the slide, there is a link. So every blue text within square bracket is actually a link to the paper. So you can go and look at that. But basically we use backpropagation through time. So you have a data set. We have a computational graph of the neuron that I'm going to go, we discretize the time in very, very tiny chunks. So nanosecond, for example, hundreds of nanoseconds. And then we have the red mechanism, the computational graph is the following. So what you do when you train with backpropagation through time, right? We exploit backpropagation as everybody does. What we need to do in order to do that, now you can imagine that at each time step, we need to store the activations of the neurons, the memory potential of the neurons, and if the neurons has output or not. And we need to do this for all neurons in the network. So we need to unfold each neuron in the network with the number of time steps that we are using. And if the time step is very small, this graph will become very, very long in time. And so it means that it will explode quickly in the memory. And so you can imagine that this is the standard algorithm that you do when you train recurrent neural networks with the traditional deep learning approach. For spiking neural network, the only difference is that you need to use a surrogate, because the activation function is a delta Dirac, or is a spike, right? And so as a surrogate model, what we typically use is Gaussian, a Gaussian shape, or a S layer, for example, uses the shape, or a linear shape, something that is that in which the derivative exists, basically. And this is very well described in Bojan thesis. And so, for example, now imagine that, and this is also true for the ECG case. So for the ECG case, so imagine that now you're streaming. Imagine that you want to classify binary images of MNIST. Time zero, you have 28 neurons that spike or not, depending whether the pixel is white or not. And then you have a fully connected layer of 64 neurons that also has recurrent connectivity. And then you have 32 output layer. So what you do, we basically send in 28 time steps. If this is my time resolution, each row of the image. And then for 28 timestamp, we record the output of the neurons. And then we train the output layer. In this case, there are only 10 neurons active to respond to the 8, right? And then we backfold, we compute the loss, we update the weights with the BPTT, etc. And so what you see there is a simulations of activity that is run, for example, in the microbrain chip. You see here, the red one are the spike coming at the input. So we have 28 neurons on input. We have 150 neurons in the middle hidden layer with recurrent connectivity. And this yellow dot represents spikes from these neurons. So time here is going vertical, and neuron ID is horizontal in this case. This is the membrane potential of one of the neurons. So in this case, neuron number 149. And then we have the 10 output neurons spike visible in this column, in this region. Those are in red. And whenever a neuron spike more than the other, it gets colored green in a certain time window, right? And so what you see that neuron 0, 1, 2, 3 spikes, 0, 1, 2 spikes the most at the beginning, but then the 3 starts firing slightly after. Then we have neuron 8, and then we have neuron 4. And now if I manage to stop it in a good point, for example, here is already 5. For example, sorry, I want to like slightly here. So we see that, for example, the network at the beginning only saw this part here, right? So this could be actually a 2, the beginning of a 2, right? And so the output of the neuron, you see 0, 1, 2, was mostly active at the beginning. But then when the network started seeing the rest of the tree, so this other small shape, it immediately switched to the 3 output here, right? And this is nice because it shows that there is memory in the network, and the network is actually using the information that is seen in order to make predictions. And so you can ask the network at each point in time, what is the output, what is the most likely class that you're looking at. And this is done with this method of backpropagation through time. So nothing novel here, just an applications of, and with this, we could actually train the microbrain chip. But now there are some algorithmic limitations here. The first one is that you need to use this straight-through estimator. So we need to use this Gaussian or whatever. And the approximation error of the surrogate gate accumulates along the time. More the sequence is long, there is also another problem, not only memory, but there's also the problem of the fact that the error accumulates in time. And so the more long is the sequence, the more error you accumulate, and the more difficult it is for you to train it accurately. And so there is also the vanishing gradient problem. Of course, this is always present, but the memory requirements that I just told you are there, and especially for asynchronous systems. And so what we did, we tried to actually Sander and Bojan, Prof. Sander and Bojan, looked at an ICML paper that was that came out a few years ago about forward propagation through time, FPTT in short. And this tries to, I will give you the intuition here, and if you're interested, you can go and read the paper, and also the thesis of Bojan, which is also linked and available online. And the intuition is that, in BPTT, what we need to do, we need to enroll all of the time step, and we need to store all of the memory. In FPTT, the intuition is that you only need to store one chunk of the network at one single time step. And you do that because FPTT optimizes an instantaneous risk function, which include a loss as the BPTT does. So a loss that is only for one time step, Plus, you have in the loss calculations, you have three terms. One term is the standard loss. Another term is the dynamic regularization penalty. And there is also an instantaneous risk function, right? So there are three functions that you need to calculate. So now we need to do more calculations per backprop compared to BPTT because we have three terms. But the memory becomes less because now the memory is only in one. And so this means that we can go and train larger and deeper network.
So quick
yes.
question here. So when you say memory is less, this is because you mean that you don't need to store the memory over all the time steps, which you have many in this case.
Yes.
But spatially, to propagate the partial derivatives forward is more expensive. Is that not the case?
Spatially, the memory is the same, right? No, the memory is depends only on the size of the network, but the computation that you do per epoch or per batch of data is more, because now you have three terms that you need. There is one average running mean, there is a risk function, and this is the loss, right? So computation-wise is a bit more expensive indeed for training, but you break basically. So the main thing is that here you break the unrolling of the network, which is very nice because that's what we needed, right? I don't care much about at this stage about the number of compute that I do per and so what it does, it lessens the memory requirement mainly for training. And so it means that we can train larger network now.
And what is the difference here to real-time recurrent learning, which has?
Yeah, so yeah, there are also other online. So this is an online mechanism for training, right? You require a label at all time step. There are other type of learning that have similar properties like EPROP, RLTL, like your real-time recurrent learning, and etc. There are differences, especially in being able to train very long sequence. But in principle, yes, it's a very good question, and I think it's worth it to explore even more now. So all these algorithms have similar scalability, I would say, for in time and in space. But this one works very, very well in very complex tasks, and I will show you one now. So also what it also requires different neuron models, actually. So it requires a neuron model that gates. And so in this paper, there are all the details about a liquid time constant neuron model that is apparently required from these algorithms, or some of the functionality are required in order to achieve very high accuracy. And so what we did actually, and what Bojan mainly did during his thesis, use this algorithm now to train a very deep neural network. And here you see a network of 6.2 million spiky neurons that has now convolution, fully connected, cross-strait parcel sum, and 40 million parameters. So here you see the backbone. The backbone is actually very similar to YOLO. So you only look one type of network. And the task that the network has been trained to do is to do object detection and identification. So basically you have to identify there is a car, there's a bicycle, there's a person, and you have to draw the bounding boxes around it. And so, and this is trained end to end with FPTT using 6.2 million spiky neurons and 14 million parameters in total. So it's a very large network. That was not possible. It wasn't fitting the GPU before with BPTT, right? So it was difficult. So now it's possible, and now this is very nice. And this actually got published in Nature Machine Intelligence from Bojan thesis. Came out, I think, a few, I don't know. Well, it was on archive for quite some time. And here you see the results of it. So you see that we're using 20 classes, car, water plant, and this is the mean precision accuracy. So it's how much of the area you cover over the, it's a measure that they use in object detection and identifications, and is approaching actually state of the art. It's not yet as DNN models, but we didn't optimize also too much for the architecture, but it's approaching it. And the fact that we can train it with FPTT, it's very nice. And here you see a small video. I hope it goes through well in the web of a street in Amsterdam in which the network is actually run. So the network actually uses RGB input. After the first layer, we convert them into spike, and then everything else is spike based. And what you see here at the bottom, you see 100 neurons from the input layer, close to the input layer. And here at the very bottom, you see 100 neurons towards the output layer. One nice property of this network is that when there is nothing interesting, towards the output layer, you have very little activity, right? So the feature gets propagated only when there is something interesting for you to see at the layer. So everything now is, it's spike-based. It's spike-based communication. It's trained end-to-end, and it's a large spiking neural network that can solve complex tasks. And so now, what's next? That's so given this and what we want to do, I think that in the coming period, there are many challenges that we need to solve, right? So this network also assumes barrier synchronizations, assumes, lots of the properties that are not very, let's say, compatible with the kind of edge AI or asynchronous systems that I like to build. But still, I think the properties of FPTT and enable us now to train larger network, and I will try to do so. And so I would like to exploit this sparse communication because the network only consumes spikes. Event-driven computation is fully event-driven, and process the temporal information. So how can we actually support this type of model, or even modify this type of model to be able to support, to be able to realize efficient dedicated hardware processors. And so this is an open challenge, of course. I mean, many people are working on it, but I think it's a very nice challenge. And now you're seeing now we are in a really exciting period because now we can do so. Before we couldn't. So when actually I started my PhD, MNIST was difficult with spiking neurons. But now looking at this and say like it's possible, so we should be able to actually exploit this type of. Yeah, so there is one question on how the input images, videos are converted into spike. For this specific network, there are 3 channels, red, green, and blue. The channels are actually inject. So let's say the color scale of each channel is, I think, 16-bit or whatever it is, 8-bit, 0 to 255. And then this is directly injected into the first layer of neurons. As a memory potential, let's say excite the memory potential, that then is immediately converted into spike after the first layer, and then everything else is spike-based. Of course, we are also working now on training the dataset from Prophecy, that is a spike-based dataset, so we don't have to do these conversions. And yeah, we have preliminary results on that, and I think we'll have something pretty soon as well in that direction.
That's what I was going to ask. Why not use an event-based dataset to?
We are because we wanted
out?
to, because we wanted to compare first with the deep learning model. So in order to be able to say this method actually works, and we want to compare it with the mean accurate precisions of other method, we need to use the same dataset. But indeed, we are now transitioning to use I call this called the Gen 4
It's
dataset.
the Gen 1 with the 380 camera. Yeah,
exactly.
also because there is a 1 megapixel one, but that's another story. It's like a 5 terabyte.
Yeah, indeed. So there is also another question. So after this input, you see, at this stage, everything else is spike-based. So everything else is spikes. And everything is binary communication here. So if you want to know more about the details, also the code is available. So if you click on the paper, there is a GitHub actually, and you can have a look at the code as well. So if you have questions about it, also contact me, but contact Bojan. He's the master in doing this. Actually, Bojan is now in Innatera, so he's actually looking at analog devices and how to use them. So let me conclude this talk also by thanking the people that actually have done most of the work. With us, so Peter Harper has done the ADC, Sander Botte the theory of the FPTT together with Bojan, Yuming He the ASC spike converter and the insertable device together with Yahong, Jan Stout and Manoli Sifalakis from IMEC. We have done this microbrain and also the follow-up chip together. And of course, this requires a lot of manpower. And now, if you are interested, you can reach out because we are interested in PhD opportunities here at TUE to work on state-of-the-art neuromorphic edge computing systems. So we have a couple of PhD openings right now, one on data flow-driven mapping, and another one on electrophotonic, which is a bit more fundamental and and I would say explorative. But yes, so reach out also if you want to do master thesis and if you're interested in the field. There is a question. No, what's the possible scenario? That's a good question. So Maxim is asking about what possible scenarios do you see for useful online learning, considering the possibility to pre-train models with BPTT and remaining need for labeled data for such algorithms? Yes, so this is actually a supervised training. So the one of FPTT, now that I showed you, but it's trained online, meaning that you still need a label at each time step. And in online training, yes, it's what type of applications do I see? I see personalization as one of them, in which, of course, you pre-train your model, and then you have your device and you want to personalize it. Could be for biomedical reasons, because everybody's slightly different. But the killer applications actually for online learning, I haven't seen it yet, except for adaptations and maybe robotics. And but those use cases are coming out hopefully soon, so that then we can actually use the online learning. But personalization in one, robotics, everything that has to do with, it is impossible to pre-train anything or any agent to all the possibilities in the world, to all of the different type of signals, noise, etc. So at some point, you will need to use online training. Of course, in industry, you might have a conveyor belt and everything is nice and settled, but in real life applications, it's never like a very controlled environment, I would say. So that could be one of the application scenario for it. I hope I answered the questions, but this, do you think that algorithm, that this is useful for reinforcement learning? Yeah, so reinforcement learning is basically, there is an agent, there is a word, there is a reward that you get from the actions that the agent perform in the word. And you need something online in order to do, to do reinforcement learning online. But I don't know if this algorithm is actually good or not for that. I know there are different algorithms that have been proposed now, but I'm not working in RL, reinforcement learning myself. So I have to think about it, honestly. I don't have a good answer now.
There's another question from the audience. And are those PhD positions available partially digitally? I do not want to move to another country these days.
Yeah, and I think this requires lab access and require to be part of a team. So typically they are here. Yes.
There's yet another one. How do you compare SNN related online learning like STTP to CNN to CNN related learning like transfer learning or one-shot learning?
So STDP has shown so far, as far as I know, poor convergence compared to backprop, and it's not the only mechanism, I would say, in biology, right, that is used to train. It's just the historically, I think it was very nice it was a very nice finding from B and Poo, and doing that is definitely one of the many mechanisms probably in biology, and so that's why it has. And we are not used, and it has poor convergence property in respect to backprop or other supervised learning method, and transfer learning, one-shot learning. These are all very nice. I mean, we can talk about those forever, but in deep reinforcement learning, we use a neural network to predict objective functions. So using an SNN would be like using any other neural network for that. Yes, it's very, very true. So I have actually a master student that is very interested in reinforcement learning and is working on inverted pendulum with FPGA. And one of the challenges that he has when he uses, for example, reinforcement learning and try to train with a neural network, right? This inverted pendulum is the reward function, engineering the reward function. because that requires a lot of effort, especially because the agent needs to know that if it is an inverted pendulum, for example, needs to know that you have to have very high reward close to the unstable but fixed point, and then the reward needs to decay otherwise. And doing reinforcement learning requires lots and lots of computation time. So you need to have a word model, you need to have a very good model of your robot, etc. And so I think it's very complicated, for sure. So, but using SNN, it will be definitely possible, because you can use, if you can do it with ANN, you can also do it with SNN. I mean, if you use a mean rate model, for example, there is a one-to-one correspondence between ANN and SNN. Maybe not the most efficient way of doing that, but definitely there is a one-to-one correspondence.
I have another one. Like when I see like people talk about neuromorphic, then I see that there is sometimes people talk about have different approaches to it. For example, like some think about it, approach it more from the side of like analog computing that relies on new devices such as memristas, and they might not even rely on spikes actually.
No.
And so you're using like this combined architecture, and so what do you think the spikes get you on your chip? Like why not just do ultra low power analog computing with a standard DNN, just optimize that? And do you think
because
is it the latency or
no, it's a very good question, but I'm interested in the long-term challenges as well of trying to understand a bit more how our the brains, or how we compute, how animals compute in general. Because if you look at the spike or at the scalability of neural systems, for example, you can find neural system in bees, neural system in elephant, neural system in all kind of different animals, and they scale very much. Not only that, but they're able to perform very incredible operations, right? With little animals. There must be something general about these systems that is actually worth exploring, and that's why I'm also driven by this field, because I think there is something interesting to figure out in it, and yeah, and going back, yes, of course, you can do that at different levels. You can do that in digital and neuromorphic with developing algorithms. You can do that in analog by trying to mimic, being really trying to mimic the physical computation that happens in the neurons in the synapse with physical elements like silicon, memristors, or whatever. And then you can also do that in an even more abstract way, just mathematically, differential equation, or you can do that in very, very different ways. And I think they're all complementary to each other in the end.
It seems like the applications that, I mean, also that you should, they need some kind of temporal element, like you showed with the biomedical signals, and then you can really exploit that as. Yeah,
in this case, yes, because of the requirement of the applications, let's say, it makes sense for us to go completely asynchronous, because of the signal properties. If the signal is, the heartbeat is sparse in time, then it makes time. But definitely, spike systems, you have to pay for the memory of the membrane potential, right? You don't have that in DNN, or you have that only in recurrent network. You don't have that for other type of models. So you need, let's say, you need to be careful of what you do with those systems, especially when you want to compare them with ANN.
Super nice. Yeah, I think thanks a lot for this talk. It was like super interesting to hear the work. Like I was honestly, I will tell you, I was actually quite excited about it up front. So I was happy when you said that you were going to give it. So that was cool.
Thank you very much for having me here, and I look forward to interact with all of you also in the next sessions of this open neuromorphic.
Great. Yeah. So this talk has been recorded, so we'll put that on YouTube if Federico is also okay with that. And
Yeah.
yeah.
Everything goes on YouTube now. Okay.
And yeah, so there's also a Discord channel for the Open Neuromorphic community. Maybe if you have further questions, then just post them there, and then we can also relay them to Federico. Maybe he's also going to have a look as well. Cool. All right, then thanks a lot. And yeah, have a nice, enjoy the rest of your day. Great.
Thank you very much.
Thank
Bye
you.
bye.
Bye-bye.
Thank you. Bye-bye.